All right, guys, video number 2 is an independence test, a chi-square test for independence. It's on the back of these notes. So just turn it right over and let's read our scenario. It says a group of second graders were characterized by their handedness and their eye color. The data is summarized here. Does this data indicate an association between handedness and eye color? The key word here is association. And the other key is that it's a single group of second graders. Unlike the homogeneity test where it was 3 different experimental treatment groups, this is just one group that we categorized into 2 different variables. So we don't call this a homogeneity test. We're not trying to look for sameness necessarily. They're trying to see if this variable eye color is associated with this variable handedness. So it's a different way of approaching it, but strangely the mechanics are going to look exactly the same. This is one of my favorite tests because it's real quick. The hypotheses are going to be that the name of the test tells you your null, so your 2 variables, handedness and eye color, are independent, is going to be your null hypothesis. Independent means that the 2 variables are unrelated. It seems to me like they shouldn't be related. We talked about this in the first couple classes. We kind of thought like, oh, does this variable have to do with that variable? But we want to use data to actually decide, not just our own personal opinion. The alternate is going to be the opposite of that. Handedness and eye color are associated. Or you could say not independent. That's fine too. I'm being lazy here with my ditto marks. Your assumptions and conditions are going to be the same as they were for the chi-square test. All your data has to be in counts. You should have a random sample since this isn't an experiment. Independence tests are not going to be experiments. It does not state that it was a random sample, it's just a group, so we're going to proceed with caution. We're going to check our expected counts in just a second in matrix B because you're going to see because it's a 2-way chart we can also use a matrix and your 10% condition. So let's go ahead and practice the calculator steps again. You should really do this with me. The first step is to go and enter your observed counts into matrix A. So go to second matrix, it's right here on the left. Go over to edit, go into matrix A, and we're going to change it. It's always rows by columns. We have now 3 rows and 2 columns, so 3 by 2. And then left to right, you're going to enter in your observed counts. So it does pretty much look like, not much of a difference whether you're left-handed and have brown, blue, or other colored eyes. Same with the right-handed. It looks like they made an other category because they didn't have enough people, and we'll see in a second with our expected counts if that's the reason why they kind of lumped up a bunch of the eye colors together. All right, we're going to quit out, and we're just going to go ahead and jump into the mechanics by going to Stat, over to Test, and down to letter C, which is chi-squared test. Don't worry about the fact that we didn't put in expected counts. We can just calculate with the observed counts, and it'll do it for us. We're going to look back at these numbers when we get to mechanics in a minute. I'm more interested in going back into second matrix, editing matrix B, and you can see it's changed to a 3 by 2, so it's the same arrangement, and it's got all the numbers that apparently are expected counts. So we're just going to be super lazy and just write down all of the expected counts that are already done for us. Again, all they're doing is that row total times column total divided by table total, but they're doing it for us, which is awesome. Just barely we made it. We needed to have 5 expected counts in every single one of our cells, and we were close on those blue left-handers, but we're good, so we can check that off of our list. All right, there's a new test name for you. The test name is the chi-squared test for independence. Your mechanics has the same 3 things that I need every time. Technically there's 4 things. Your expected counts are part of your mechanics, but we just wrote them up here. Next, we need our chi-squared score. You want to write the formula out, and it's on your formula sheet. And then you're just going to let the calculator do all the work for you, unless you really feel like subtracting, squaring, and dividing. I don't need to see work for it. I just need the answer. So we're just going to go back in, because I deleted it, or it cleared out, and calculate. Apparently the chi-squared score is only 0.708. Remember, that's a test statistic, it's not a percentage. So it's not even a full chi-squared score over. They've also calculated my p-value for you. Now that is a percentage, that's 70.2%. And they've told me my degrees of freedom are 2. Again, that is rows minus 1 times columns minus 1. So in this case, there were 3 rows minus 1 times 2 columns minus 1, and once again, we got 2. So new formula, you really got to have that one memorized. My p-value notation is what is the probability of getting a chi-squared score greater than this chi-squared score that we got, which wasn't that big of a difference, and we got 70.2%. All right, that's it. Now we just need to decide whether we have significant evidence to reject the null, and I hope we all agree we do not. This is a very, very large p-value, so we need to say because the p-value of 70.2% is greater than alpha equals 5%, we must fail to reject the null. Be careful here, guys. We have just now said fail to reject. That does not mean we've said the null is true. It means really nothing. It's possible that if I took a different sample, or it was random, or a larger sample, that maybe there is an association. That's not something that we're allowed to use our data to decide. We can see, though, that we got pretty much what we expected in our observed counts. So that's why we ended up failing to reject, because it wasn't significantly different, the numbers that we see here. So we have insufficient evidence of an association between handedness and eye color. And that's it. We don't need to say anything about the differences that we see. For one, there aren't really big differences because we failed to reject, and also we don't want to sound like we're contradicting ourselves by talking about differences. Pretty much there doesn't seem to be any difference between whether you're left and right-handed and what your eye color is, but we can't be sure because, again, we've failed to reject. All right, that is a chi-square test for independence.